Good morning, everyone. Welcome to the webinar. Today's topic is PV Elite webinar, how to use PV Elite for simple re-rate. Our panelist today is Ray Delaforce. A quick reminder before we start to everyone, everyone's muted by default, so if you have any questions, comments, you can type them in the questions tab. And with that, I would like to introduce Ray.
Morning, everybody. Can everybody hear me?
Yep.
Okay, thank you very much. Hoping I can. Just excuse me a moment, I have to just start this again. And can you see my screen?
Yep.
Okay, thank you very much. Okay, today we're going to consider re-rating a vessel. It's a very simple exercise. Most of you will intuitively know how to do this. So this presentation this morning might just serve as a reminder. My name is Ray Delaforce. I'm an engineer at Intergraph, and I deal with the program and I deal with technical support as well. So let's get into this discussion this morning. We know that vessels can deteriorate over time. They suffer from corrosion. We can see corrosion in here. I don't know what this vessel is. I don't know the history of this particular slide. But we can see that these two inspectors are inspecting damage or, we say, corrosion in a vessel. So there are various types of corrosion. There's some external corrosion on a vessel. And there might be some other damage as well. These are just as very, very simple examples. Of course, there's no point in wasting time on certain vessels. We can look at this vessel, for example. Now, this is a very, very unhappy vessel. This vessel obviously, well, actually, indeed, it suffered a fracture during the hydro test. And does anybody know what type of fracture this is? You can look at the fracture face up here, which should give you a clue what's happening here. Sorry about that. Okay. Do you notice this fracture face is at 90 degrees? It's not at 45 degrees. This indicates that this is brittle fracture. Now, brittle fracture is not the subject of this discussion, but I just thought I would mention it as a point of interest. Sometimes shoddy work is the thing that we have to encounter. Now, anybody who knows anything about welding will know that this welding really is a very, very poor specimen indeed. There's underfill there. It's badly done. This is obviously a manual weld. This is a stick weld or SMAW weld, and it's very badly done. And you know, I was a vessel inspector at one stage of my life, and I certainly would not pass this weld. So we can have a look at the sort of inspector that actually passed it. Here's the inspector, and actually he had another eye patch as well. So as you can see clearly, there are some vessels that don't even get out of the starting block. Now we consider re-rating a vessel. There are a number of reasons why we re-rate a vessel. It might be a change in temperature. We might want it in service to experience a change in pressure. The vessel may have suffered some corrosion or erosion or metal loss. A repair has been done. We have to reassess the vessel after repair. Now, there are any number of reasons why we would re-rate a vessel. We're just going to consider really one reason during the course of this discussion. First, we consider metal loss. Everybody knows that if you leave a piece of iron out in the rain, it suffers rust.
They're not seeing your screen. Okay, there you go.
I'm terribly sorry, I didn't realize it. I'm going to go back. Okay, we can see vessels deteriorate over time. No point in wasting our time on some vessels. Just quickly show this to you again. We have a 90-degree fracture face. This is an indication of brittle fracture. As I said, This is not the subject of our discussion this morning. I just thought I would mention it out of interest. Sometimes we see shoddy work. We can see that this weld is very, very badly executed. We can have a look at, maybe this is the inspector that passed it. Maybe he was completely blind. So we can see that some of this work shouldn't really get out of the zoo in the first place. It should be left in the workshop. Now we consider re-rating a vessel. There are various reasons why we would want to re-rate a vessel. Perhaps there's been a change in the surface temperature, a change in the temperature. The vessel may have suffered some corrosion or erosion. Over time, vessels do suffer to some stage or another. Perhaps a repair has been done. We know if we leave a piece of iron out in the rain, it will rust. Obviously, the products of corrosion, which is really an oxide, reduces the thickness of the metal. And there may be products inside a vessel which will cause corrosion to occur, and we would get a vessel that actually gets thinner over time. First, we consider metal loss. Okay, you might not have seen it in this particular way, but metal loss falls into two categories. Okay, predictable and unpredictable. Now, what I mean by predictable and unpredictable, how can you predict anything? Well, predictable corrosion loss means that the rate of corrosion is a known quantity. This occurs at a steady rate over time, so many millimeters per year. And the corrosion perhaps will be experienced generally over the whole of that internal or external surface. And we will be able to predict this. So internal inspection periods can be predicted. For example, if it takes maybe 20 years to lose all the corrosion allowance, we could perhaps have the inspection periods every 8 years or something like that. Now we look at predictable metal loss. We just consider an example here. A regular inspection, the corrosion is monitored, and we have a history perhaps of similar vessels in service, and from this we can determine the amount of metal lost over time. So we can predict how much metal is lost per year. But of course we would need documentation. Very important that we would have inspection reports available to us. So we just consider an example. Let's just consider an example where we have a particular vessel and it has a corrosion allowance, should we say 4.5 millimeters, 4.5 millimeters. We may know the rate of corrosion over time because we've monitored the corrosion as it has progressed through the years. And we just determined that, well, the corrosion allowance is 0.23 millimeters per year. Remember, this is general metal loss, and it's predictable. So the time to exhaust all the corrosion, we can figure this out. We take 4.5 millimeters and divide it by the corrosion rate, and then we say, well, we can use this vessel for another 19.5 years. So we can say, well, we'll set the inspection period just arbitrarily to every 8 years. So we'll monitor the corrosion rate, just see that it's still steady. Because we need to establish the corrosion rate is steady. So regular inspections are required. Never consider unpredictable corrosion loss. Okay, we discover there's an area where there's been a little bit of corrosion in one area on a vessel. And that's a little bit troublesome because we want to know if we can still continue to use this vessel. Now, from an inspection report, we know the current thickness, we know the original thickness, we know the current thickness. So we've got to use some procedure to make a determination as to whether we can continue to use this vessel in service, whether we to do a repair, or whether we have to scrap the vessel, or even reduce its working pressure. One of the tools that we can use is API 579, and that can be used to assign a new thickness to the vessel. We know perhaps we measure a vessel, we know that its minimum thickness is so much in one place, but do we use that thickness in the calculation for the maximum allowable working pressure. And API 579 doesn't actually use the minimum thickness, it uses a sort of average thickness. But we need a procedure to determine what that average thickness is. Now, during a routine inspection, perhaps a patch of corrosion is found. This might be internal or external, but more likely with internal corrosion. The external part of the vessel is not usually exposed to the corrosion products inside the vessel, so we may see a patch. We find, there we are, there's a patch. This is actually inside the vessel. And this little patch, we can see this means some sort of generalized, it's not pitting, but it's generalized corrosion over that area. It might be because a pipe on the other side, a nozzle on the other side is passing products into the vessel and is wearing away the vessel on the opposite wall. It could be any reason whatsoever. So we need a procedure to determine whether this vessel can continue to be used in service. So let's look at the survey method for a moment. First of all, we need to identify the corroded area. The inspector would go inside the vessel. With an inspection, he's determined that this area of the vessel has been subjected to some corrosion. Okay, he's identified it, so he has to identify that area. Now we have to determine what we have to do about this corroded area. So what the inspector can do with a pen or a marker of some description, he can overlay a grid over this corroded area. Do you notice that the perimeter of the grid, oh man, I can't get the, I can't show, there we are, I couldn't get the pointer. If you look at the external perimeter of this grid, it includes areas that are uncorroded. We need that to monitor so that we do know that we have this corroded area completely confined within this perimeter. Very, very important. Now, it sounds quite easy to do, but don't forget that an inspector may be standing on a ladder and he's trying to mark this grid on the vessel. So it's a difficult job, but nevertheless, this is one of the procedures that's available to us. So we mark this grid on the vessel in the circumferential and the longitudinal directions. We're just assuming for a moment this is a cylindrical shell. So there we are. These represent the circumferential direction, and this represents the longitudinal direction. Now, of course, you do know that the circumferential stress, or the hoop stress, is twice the axial or long stress in a vessel. So the corrosion in the longitudinal direction is very important. Now, the next thing we do, we measure the thickness of every node. So let's look at node points just for a moment. Now we have these nodes, and we measure the thickness at every single node. So we make up a table. Now we just tabulate the results. So we set out a table, and maybe a table looks like this. I'm extremely sorry for this small spelling error. I only found it this morning. So now we find the CTP for the circumferential thickness. There we are. CTP is the critical thickness profile. First of all, in the circumferential direction, we find the minimum thickness. And there it is. If you look along this line here, you'll notice that this is the thinnest point. All these points on the line, and we just mark that point in this here. And then we look at the minimum thickness in the longitudinal direction, and I've chosen this point. And if you look at all these points down here, you'll notice that this is the thinnest point. So we can put that number in there. Now, of course, we can complete the table using the same procedure. So we just complete the table, and it will look something like this. And what do we do after this? Well, we've got to determine the minimum thickness for a start, because that's the area we're most interested in. That is the minimum thickness in the whole table. Okay? Now we can create a profile of all the thicknesses along this line. Okay? How we do this? Well, it's done like this. There's the profile along there. Obviously, we just use straight lines. These represent the thicknesses at each node. We find the thinnest thickness, and we consider the thicknesses either side of that. Now we plot the profile. Now we just include the corrosion that we want for future use. It might be 1/16 of an inch. And from this line here, we work out an average thickness. I'm not just going to tell you how to do this, but there are various ways of calculating the average thickness. And we find here that the average thickness, should we say, is 0.492 inches. So if the future corrosion allowance is 0.0625, then the thickness at which we base our calculation is actually this thickness here. I'm not going into all the details. I'm not discussing API 579 in depth. There's perhaps other seminars that deal with this. There may be severe pitting. Okay, we find pits all over the place. They're just little craters that are corroded in the metal. And the spacing has to be important. You get spacing between critical craters. And the depth of the pitting may be very important. I'm not going into great details. I'm just discussing in general terms. And we can actually measure the depth of those pits, perhaps using a welding gauge. This is known as the Cambridge welding gauge. It's based on a British design. This protractor here, this pointer here with this little beak here, can be actually turned around, and we can determine the depth on this scale up here. So we know the depth, we know the diameter, we know the location of the pits. And from the spacing, size, and depth of the pits, we can get some average thickness we can work with. We just simply deduct the future corrosion allowance so we can calculate the MAWP. Now let's use PV Elite to do a re-rate for us. So let's just use a hypothetical case. Now we have a vessel, and the as-new material, or the as-new data is like this. We've got a material 516 grade 70. The design temperature was 300 degrees. The MAWP was 250 psi. The diameter was 72 inches. Thickness was 9/16. The original corrosion allowance was 0.125, and the weld joint factor is 0.85. Now, we want to re-rate this vessel, but using the current conditions. Okay? So we're going to perhaps downgrade the pressure from 250 down to 240 psi, but we're going to raise the temperature from 300 to 450 psi. And the current thickness, the average thickness that we've calculated using some, maybe API 579, is 0.52 of an inch. Remember, the original thickness was 0.5625. And the corrosion allowance that we want in future is 0.0625. Now, this is a very, very simple process as far as PV Elite is concerned. Let's just have a look exactly how this is done. Here's the calculation performed by PV Elite. Okay, we've got our cylinder in there, we've got our pressure, we've got our temperature, we've got our corrosion allowance. They're all there. And so we do the calculation. If we look at the status line down here, we notice that everything is in black. If any thicknesses were insufficient or the MAP was insufficient, it will be shown up in red. So we know that's okay. So we got the MAWP. Now it's more than 240 psi, which we require. The thickness is okay. It's less than 0.52. So we have a little bit of extra material available to us. So we now can compute the future life of this cylinder. Let's have a look at this very, very simple calculation. The minimum computed thickness according to PV Elite, this is minus the corrosion allowance, is 0.4896 inches. The minimum thickness as measured when the inspector went in the vessel and did the calculation using API 579, he determined that the thickness was actually 0.52 of an inch. So that's thicker than that, and the difference we have available for future corrosion allowance. So we can compute the corrosion allowance. So there is the actual thickness, and then don't forget this thickness includes the corrosion allowance in PV Elite. So we deduct the corrosion allowance to get the minimum required thickness of the metal without the corrosion allowance. So there it is. Now we can calculate the amount of metal available for future corrosion allowance. Here it is. Take 0.52 of an inch, the actual thickness, actual average thickness. Okay, we deduct the required thickness according to PV Elite here, and we see that we have 0.0929 inches for future corrosion. Okay, we already know from some source, I don't know where, but from some source, this is just an arbitrary number, but we know that the future corrosion will actually proceed at 0.017 inches per year. Now we can predict the future life of that vessel. The future life expectancy will be this thickness. This is the corrosion allowance, divided by the corrosion allowance or the corrosion rate per year, and we see that this vessel can last us 5 years. Okay, that's the life expectancy. This gives us plenty of time to, make a plan in the future either to replace this vessel, to repair this vessel, to scrap this vessel, or even to downrate this vessel. We might use it in another service. Re-rating is a very, very easy process, but it has to be done very, very careful. For example, you must keep careful and accurate inspection records. You must keep your PV Elite models on file for future use. This is very important. And if you do these calculations for the same vessel over the various years, you must know when those calculations were done. Do the calculations carefully and keep the results as a history of this job. And make sure that key members of your staff have all this critical information, because somebody somewhere has to make a decision as to whether we use this vessel in the future, whether we scrap this vessel, whether we repair this vessel, whether we downrate this vessel. They can only do it if they have knowledge. That's very, very important. Knowledge. And documentation. There may be cracks in the vessel. Now this is API section 9. We're not dealing with this in detail, but cracks have to be assessed. We might have this crack in a biaxial stress field. We might have stresses. This might be the longitudinal stress, okay, and this might be the hoof stress. We find a crack in a piece of metal, and there are various things we need to know about this crack. We might need to know its angle. We might need to know its depth and the thickness, its depth from the surface. This is perhaps the outside surface of the cylinder overhead, and this might be the inside surface. So API helps us to assess these thicknesses, to assess these average thicknesses. CodeCalc at the moment is undergoing a bit of a facelift as far as API 579 is concerned, but some of the level 2 calculation can still be done in CodeCalc with that grid system that I showed you a little earlier. So ignoring the effects of cracks in a vessel, we ignore the cracks just for the moment because we don't have the procedure in CodeCalc. Re-rating can be a very, very simple process, both for generalized corrosion over an area or perhaps for pitching. And even models as complicated as this can be re-rated. So I thank you for your attention, and it's been a privilege for me to present this to you. You may have some questions that are going to be asked, and they will be relayed to me.
Thank you very much, Ray. Everyone, if you have any questions, you can type them in the questions tab. We'll take those now.
Are there any questions?
Yes, Ray, there's one question. Someone's asking, how can they identify whether a vessel will last 50 years or not?
They would need to know two things. They would need to know the current thickness, okay? They would need to know the minimum thickness, and they would need to know the rate of corrosion. So if we get the amount of material that is available for corrosion, let's say, as in my first example, you had the minimum calculated thickness of a vessel, should we say, is 10 millimeters, okay? But the actual thickness, should we say, is 12 millimeters, the average thickness. So that means that you have 2 millimeters to play with for future corrosion. If you know the rate of corrosion, should we say 0.1 millimeter per year, you can take the corrosion that is available to you, which is 2 millimeters, and divide it by the rate of corrosion, which is 0.1 millimeter per year, and you would end up with a life of 20 years. This is only available if you know the rate of corrosion and it's predictable. If it's unpredictable and you've got, various patches all over the place that are corroding, you cannot use this method for predicting future life.
Okay, thank you, Ray. There's another question. Is there any crack assessment currently planned for PV Elite?
That question will have to be fielded by Kristin. She is our materials expert, and she's dealing with API 579. So if she has a comment, she will have to give it. I do not know the answer to that question. I'm sorry.
And looks like one more question for you, Ray. Can you change the X-ray status of the original vessel?
Yes.
If it was originally spot, can you do additional X-ray and joint efficiency?
Provided you adhere to all the rules of the ASME code, I presume you're talking about ASME, and the AI, the authorized inspector, will allow you to do this. You can certainly do this. My experience has mainly been in South Africa, where I was the authorized inspector, and I would regularly allow a person to increase the amount of radiography. However, there is a danger in that. If you start doing full radiography, you might find problems in the welds that you haven't identified when you originally did spot radiography. So that's going to force you to do some more repairs on the vessel. So you have to use that system very judiciously.
Okay. What is your advice in order to get a confident rate of corrosion?
The only way you can do this is by regular inspections of a vessel. Now, there are other methods as well. For example, you can put a little piece of material welded to the wall of the inside of the vessel. Should we say, let's say you take a little round rod and you just tack it to the inside of the vessel very carefully. Now, what you can do over time, you can actually measure the rate of which the metal wastes away over time, and you can monitor this, you say, maybe every year if you've got access to the inside of the vessel. And in this way, you can assess the rate of corrosion if you state that the rate of corrosion is the same as the corrosion of that little sample that you weld into the vessel. Otherwise, you're going to have to do a survey. But the other method is you find a particular part of the vessel and you constantly monitor its thickness, provided when you look at the vessel as an inspector that you see that the corrosion is generalized. In other words, it's corroding uniformly over time. And this is the only way of getting the rate of corrosion. It's a black art.
Okay, and we're going to take one more question. Can you do a re-rate if the build data of the vessel is not available?
Yes, this is done constantly. The only trouble is you don't know the material, okay? So it may be you'll have to find a piece of the material of this or try and get the history, but let's assume you cannot get the history. Let's assume there isn't a nameplate on the vessel even. You're going to sort of do a survey completely from scratch. You have to measure the diameter, the length of the vessel, get all the details of the nozzles, the reinforcing pads, and then you'd have to do a thickness survey, and you'd have to try and estimate what that material is. If you've got a piece of material that you can sacrifice on the metal, you might take that down to the laboratory. You would have a chemical analysis, okay, and perhaps mechanical tests. And you can say, well, this is equivalent to 51670 or SA285 grade C. If you can get this information somehow, then you can calculate the MAWP of that vessel, but you need a thorough survey. I've done this often in South Africa, where I've done a thorough survey of a vessel, and then I'm going to do the calculations, work out the corrosion allowance, and said this vessel could be operated with an MAWP of, should we say, 100 psi, whatever.
Okay, thank you very much, Ray. Thank you very much, everyone, for joining us, and we hope to see you at the next webinar.